Thank you. And thank you everyone for coming. My name is Alexander Janssen. I am a digital archaeologist from Leiden University. And I will be giving a presentation on a comparative assessment of four space syntax methods by applying space syntax to a city block, Insula 5.2 in Austria. So, over the past few decades, space syntax has already proven to be of added value for archaeology. However, the method itself remains relatively inaccessible and underused. The fact that the handbooks which are written, there are many, are aimed generally towards architects or urban city planners doesn't really help with this problem. On the other hand, the number of unstudied case studies continues to increase, mostly from geophysical research, which are very suitable for this kind of analysis. So we should really start using this more, because it allows us to get the most out of limited data. Now, as this is one of the first presentations this conference about space syntax, I will try to give a very brief introduction on the subject. Now, space syntax as a whole is a collection of theories and methods for spatial analysis, with the methods being the toolkit. Now, it is generally used to understand and predict how present-day cities use by architects and urban city planners, but it can also be used in archaeology to retroactively predict how it would have worked in the past. Now, the methods allow us to study the relationship between syntactic parameters and social variables, but this will become clear later on. Now, in order to reconstruct or try to learn as much as possible about the daily lives of people based only on the architectural remains, the best way is to combine multiple methods. And these are the four methods that I will discuss in this presentation. So first, we have axis analysis. This allows us to study interaction in convex spaces. Then we have isovis analysis, which allows us to study the visual field from a single point in space, which is very similar to viewshed analysis. And then we have visibility graph analysis that allows us to study the visual properties of all spaces, so you generally get averages for every single space. And lastly, agent analysis, also known as agent-based modeling, which is used to simulate and study pedestrian movement. So the main research question I'm posing in this paper is which of the four selected space syntax methods are of the most explanatory value for the analysis of changes in urban buildings, taking the required time and effort into consideration. Answering this question allows us to create a groundwork which is suitable for archaeologists. And the data set with which I would like to answer this question is based on my master thesis in digital archaeology. In order to answer this question, I will compare two construction phases of a city block in Austria with each other. My case study lies here, the red marked area. It is located in Ostia in Italy. Now, Ostia was the harbor city of Imperial Rome, and it is located at the mouth of the river Tiber, so quite close to Rome. Although nowadays the shoreline has moved a bit outwards due to 2,000 years of sediment disposal by the river. So this is what my case study looks like now, or 3 weeks ago. As you can see, most of the walls are still standing, and in some parts even ceilings have been preserved. The data set which I use is basically this plan combined with the plan of the other phase. Now here you can clearly see that the insula is divided into 14 different buildings, although this one is counted as 2 buildings and that one's counted as 2 buildings, so technically 12. I chose this insula because it is a very diverse insula. There are a lot of different types of buildings. So for example, you have here a row of shops, a storage house building, an apartment complex, a domus, a bathhouse, another domus, a workshop, a house. We're not sure yet. It's a bit damaged, so we don't have much remains. Another house, a workshop, another apartment or house, and lastly a storage building, probably for those shops. To give you a bit of a more detailed look at the buildings, on the top left you can see the Domus del Portiro, or the House of the Porch, which was probably owned by a wealthy merchant, either from Austria or from nearby Portus. On the bottom left you have another domus, which may also have been owned by merchants. On the top right you have the apartment building, which I included because it has a very complex but interesting internal layout. And in the bottom right you can see the bathhouse. Now I also made, it wasn't really part of my research, but I also made a 3D reconstruction of how it looked like around 400 AD, based mostly on drawings from the 80s by Johannes Boersma, who conducted extensive research on this insula and also created the plans that I'm using. Now it also includes the, as you can see in the top right, not sure how clear it is, but in the transparency, the internal ground floor. And I just want to say that if you really want to get into your data set, then creating a 3D model really forces you to rethink and think about it better. For me, it's helped me a lot with my interpretations of my data. Now, the first method that I will be discussing is axis analysis. In this method, you try to transform the plan of the building into a graph consisting of nodes and connections between them. Basically, every node represents a single space, or convex space, as they're technically called. And the connections between them show how they're connected through doors, passages, etc. One notable thing is that there's one node that represents 4 streets surrounding the insula. So that's why we see lines going all across the image. Because that is considered one unit public space from which you access the insula. Now, the graph in the previous slides results in a justified axis graph with the street being node 0000 at the bottom. Already from the shape of the graph, you can already learn a lot of things. So first, it is very shallow in the sense that it has 1, 2, 3, 4, 5, 6 layers of depth, meaning that in order to reach the deepest space in the highest level of the graph, you only have to pass through so 1, 2, 3, 4, 5 other rooms in order to reach it. Which is an indicator of accessibility and privacy, which at the top would have been low, and at the low accessibility and high privacy, and at the bottom low privacy and high accessibility. At the same time, it is bush-shaped, meaning that it is very wide and shallow, which reflects the number of connections to the streets. So out of all spaces, which in our 137, I think, in this phase, 47 are connected directly to the streets. So accessibility during this time period, this Farron phase, was much better than we will see during the other phase. And this accessibility can be also an indicator of commercial activity. So during this phase, you would expect more commercial spaces in my dataset. Now the second phase, so this one is around 400, 500 AD, the final phase. Around this phase, you can see that the graph has become much deeper. There are now 11 levels. It is still somewhat bush-shaped, but slightly thinner, so lower accessibility with a few, there's like 3 less connections to the streets. But more importantly, you see a very high increase in complexity, especially in the deeper levels of the graphs, with the graph now being more top-heavy, reflecting that the insula became inwards, focused inwards. Now, with those graphs there, you can generate a lot of data for every single node, but this is just a presentation of 50 minutes, and I have to discuss four methods. So this is just to give you an impression of what kind of things you could do with the data and graphs you can make. So the second method is isophist analysis. Like I said, this is very similar to viewsheds. So in this case, I systematically created a isophist from every single entrance to give us a outside perspective. But you can do it from any location you want. The advantage is this method is very easy to interpret. This is the result. All you have to check is, does the size of the isophist increase between one phase or another? And if there are elements or parts of the building you're interested in, are they visible or not from the street? Now, the disadvantage of this method is that it is relatively subjective because you place the isophist yourself. There's no guidance. So if you want to do it in an objective way, you really have to systematically place them and have good arguments. So this is an example of the size comparison between the isophist, the same isophist during the different phases. And you can see most of them decreased in size, reflecting that a smaller area of the insula was visible from the street during the final phase than during the third phase. Now, the third method is visibility graph analysis. You can generate a lot of different layers of data, but in this presentation I will focus on intervisibility because it's the easiest to explain. What you get here is a heat map of the insula, showing the red areas are areas which are highly visible, going down to green to yellow to blue, meaning areas which are visible barely at all from other areas. Now, as you can see, there is a clear decrease in visibility, reflecting an increase in privacy. I also included the streets, which was for two reasons. One, study the effects of the streets on the internal space of the insula, and two, because I kind of didn't have a choice, because I wanted to do an agent-based model and all spaces have to be connected to each other in order to do that. So it was also a bit of a technical reason. Here again is an example of a graph you can create of the visibility graph analysis, a simple box plot showing that the mean visibility decreases. Now the final method is the agent analysis, or agent-based modeling. Now this kind of model allows us to simulate pedestrian movement. Which is done by setting free autonomous agents from random locations within the accessible area without giving them any goal or purpose. They're simply instructed to walk around. Now, this is not entirely random because it is based on the previous methods, visibility graph analysis. The agents are allowed to use the data of the cells from the visibility graph analysis in order to select their next preferred destination. And this allows us to realistically, at least for modern architecture, to realistically simulate pedestrian movement. This has been tested a lot and compared with actual people. But for archaeology, at least in my opinion, what these results represent are not if people actually went there or not, but the urge of people, if they are, how much they are attracted or drawn into a certain area. So for example, you have here a storage building where you wouldn't expect people to randomly walk into a storage building, also because it may be locked. That's also one problem. We don't know if there were doors or not, so that's a bit difficult. You have to assume, in order to be able to run this analysis, you have to assume that the doors were either open or that there weren't any doors. And so to conclude, which of the four selected space image methods are of the most explanatory value for the analysis of changes in urban buildings? Well, My favorite method, the one I would recommend the most, is axis analysis, because whilst it can be potentially complex based on how much time you want to put in it, you can make a very high number of graphs. You can make graphs showing the averages of every single building, of every single space. So it really depends on what you want, but it is quite efficient. You get you can provide many new insights, and you get a broader range of interpretations. So I highly recommend it. So the second one that I would recommend is isophysics analysis, because whilst it's simple, it is quite efficient. You can do the isophysics analysis theoretically in a few minutes, and at the same time, it is also very easy to understand for non-specialists. All you get is something visible or not. So it's very easy to present. However, it is the least objective method because of the placement of the nodes. They have to be done manually. But I still recommend it. However, the visibility graph analysis, at least for the study of change, I wouldn't recommend it. Because, well, it is very complex, but the results you get aren't really worth it in a way. They're not as many new insights compared to the axis analysis, but the axis analysis is much simpler. So with visibility graph analysis, you get an abundance of data, which, well, if you have a very small data set, it may be great, but if you begin to, so even already at my size for 14 buildings, it was already on the upper limit of what you can do. And at the same time, it is difficult to use and to interpret. So for the study of change, I wouldn't recommend it. And lastly, you have agent analysis. What the disadvantage of agent analysis is it requires a lot of theoretical knowledge about how the agents work, how they are programmed, in order to avoid the so-called black box effect of not knowing why the agents go somewhere. Well, depending on if you like a lot of data or not, it generates less data than VGA. So I consider that as a benefit, because visibility graph analysis really gives you too much data. But the advantage of agent analysis is that once you have done the visibility graph analysis, well, this is done in the same software, so you already have the exact data set you need. All you have to do is click a button, run the analysis, and you have the agent-based model. So if you do visibility graph analysis, then you might as well do agent analysis.